Alright, so what is electric flux and what is Gauss's law? So, whoa, what happened here? Okay, so first we're going to review magnetic flux. We're going to review magnetic flux from last year. So if you have a bar magnet, that bar magnet has an invisible magnetic field around it. If you place a tiny imaginary compass right here, that compass would swing around and it would end up pointing this way. And the way the tiny imaginary compass points, that's the way the invisible magnetic field is going. And if we did this for all points around that bar magnet, we would find that the invisible magnetic field looks like this. And we remember that here, the field lines are closer together, and where they're closer together, that's where the field is stronger. And then out here, the field lines get farther apart, so the magnetic field gets weaker. Where the field lines are closer together, you get a stronger field. Where they're farther apart, you get a weaker field. If we took two bar magnets that were anchored down, two anchored down bar magnets, and then we tried to figure out, oh, what does the invisible magnetic force field look like in this area between the bar magnets? We can play that same game. We can pretend to put a tiny imaginary compass there. If you put a little compass there, the little needle would swivel around, and then it would end up pointing towards the south. Because the north pole of the compass is the direction that the compass is said to be pointing. And that little baby north pole of the compass would be attracted to the south. Thus, the magnetic field lines would be going across like this. North to south. And that helps us visualize the invisible magnetic force field between those two anchored down bar magnets. What's that? No. The compass is just a little baby bar magnet that's free to swivel around. So it's a little bar magnet that has its own north and south pole, yes? So this might be like a little south pole of a little baby bar magnet, and this might be a little north pole. And if you put that right in here, which way is that little baby bar magnet going to swivel around? Which way would the north pole end up pointing? Towards the south. And whichever way that little baby north pole points, that's the way the compass is said to be pointing. That's why, usually like Boy Scouts compass, they make it into an arrow. But the arrowhead side, that's the north pole of a little baby compass needle. And it points towards the south because it's attracted, because opposite poles attract. So the weird thing is, and maybe this might be confusing you, if you take a look at good old Mother Earth, and up here is the geographic North Pole, and down here is the geographic South Pole. Well, basically, compass needles were named after which way they point. So if you take a piece of lodestone, which is like a natural bar magnet, and you hang it from a string and you allow it to freely swivel, so here's my rock, my lodestone rock, yes? And then I hang it from a string. So this is like from the ceiling from a string. Of course, it's not drawn to scale, just to help us out here, right? Okay, when it swivels, one side of the lodestone naturally points up north. By definition, the side that naturally pointed north, they called it the north side of the lodestone. No. It's defined as the north side, the North Pole. The side that points north is called the North Pole. The side that points south is called the South Pole. And that's how all bar magnets are originally identified. You allow it to freely swivel, the side that points up north, by definition, the north-seeking side is called the North Pole. But then, if you remember, if you have a bar magnet that's swinging here, and this is the North Pole and this is the South Pole, and then you take another bar magnet and you allow it to swivel, what pole is going to be over here attracted to that north right here? A south. We know that opposites attract, yes? So basically, this is going to be a south pole because opposite poles attract. So now going back to the Earth scenario, and this is where like a lot of people get confused. Right. This scientist by the name of Gilbert, he's the first one who realized, holy schmoly, the Earth itself acts like a big bar magnet. The Earth itself is like a big bar magnet, but the weird thing is, the poles of the bar magnet don't even line up perfectly with the poles of the Earth. It's like slightly off, so it's more like this. Not only that, up at the geographic North Pole, it's the South Pole of the Earth as a bar magnet. And down here is the North Pole of the Earth. And then again, if we draw the invisible magnetic field lines around the Earth, by definition, whichever way the tiny imaginary compass needle points, that's the way the invisible magnetic field lines are going. So over here, which way are the invisible magnetic field lines going? Well, if that's the North Pole, then it's going up there like that. So the invisible magnetic field around the Earth, the field lines go up here into the south, down here, around like out to here. Out here, around, into there. Does that help clarify things a little? Okay. Okay, so going back to our bar magnet like this, if I take these two bar magnets and I change the orientation, I pick them up and I pick them up. Here's the two bar magnets. I pick them up like this, yes? And I change the orientation like this. Which way are the field lines going to be going now in between the two bar magnets? Into the board. So I pick up the two bar magnets and I put it like that, so now they're going into the board. I'm not even going to draw these bar magnets anymore. I'm only going to draw the magnetic field lines. So here we go. To draw those magnetic field lines, they're going into the board. Now let's say I have another set of bar magnets and I position them similarly to this. And the invisible magnetic field of the other bar magnets look like this. Those are the invisible magnetic field lines going in between the bar magnets. So here is the invisible magnetic field between another pair of bar magnets. What? Now in both cases, 4 magnetic field lines are shown, but are those fields the same strength? If not, which field is stronger and how do you know? Are they both the same strength? Man, chat.
The top one is stronger because the lines are closer together.
That's what I'm talking about, people. Remember over here we said, oh look, when the lines are closer, the field's stronger. Over here where the lines are farther apart, the field's weaker. Well, look over here. Here the lines are closer together. This is going to be a stronger field. Here the lines are farther apart. This is going to be a weaker field. So what we need to do is make some measurements and describe how to calculate the strength of this invisible magnetic field. So here we go, people. Hold on to your seats. All right, so the number of magnetic field lines is also called the number of flux lines, because a flux line is synonymous with a field line. So over here, if I said, oh, how many magnetic field lines do you see? Well, the same question is, how many magnetic flux lines do you see? And the symbol for magnetic flux is a Greek symbol, phi. I think it's actually like this, capital phi. And you can say, oh, how many field lines do you see there? 4 magnetic field lines. But another way of saying that, you could say, oh, I see 4 magnetic flux lines. Synonymous. Or, to honor another scientist's last name, no, also a grill name. Most popular grills in America, known for their quality. Barbecue grill. A Weber. Anyone here have a Weber grill? They're known to be like one of the best. They're very expensive. Weber. Barbecue grill, Weber. Go to Home Depot. Look at the price of the Weber grills and the price of the other ones. No, grill. You guys are thinking about girls. You should be thinking about physics. All right, it's on the recording. I will check tonight. Right now, let's go check it. 4 Webers. Or you can say 4 about grills, has anyone heard of Weber grills? Thank you, thank you. Has anyone heard of Weber girls? All right, see, that doesn't make sense. Except for Andy. Now notice, if I call this the amount of magnetic flux up here for number 1, well, down here for number 2, how much magnetic flux are we dealing with? How many flux lines do you see there? Still 4. 1, 2, 3, 4. 4 Webers. 4 flux lines. 4 magnetic field lines. But we know that the field on top is stronger. The field up on top is stronger because they're closer together. So to get the strength of the magnetic field, what do you have to do with the number of flux lines, Jordan? Divided by the area that the field lines are going through. You remember this, folks? Magnetic field strength, symbol capital B, is equal to the number of flux lines per area. Because if it's in a smaller area, you're going to have a stronger field. So let's just put some numbers on here. Let's say this is 1 meter by 1 meter. These are nice baby easy numbers. I know ridiculously big, but that's okay. And let's let this be 2 meters by 2 meters. If we go to find the strength of each of these invisible magnetic fields, we come up here and we say, hey, how strong is that magnetic field number 1 up here in the top? Well, it's equal to the amount of flux lines divided by that area up there. Well, how many flux lines do I have? 4 Webers. And what's that area going to be up there? 1 meter times 1 meter, which is going to be 1 meter squared, length times width. So this is going to be 4 Webers per meter squared. Now, since it's kind of telling you like how dense the field lines are, it's also called magnetic flux density. That's right, magnetic field strength is also called magnetic flux density. And the magnetic flux density of that top sucker up there is 4 Webers per meter squared. But wait, there's more. To honor another scientist's last name,
Wow.
Tesla. 4 Tesla. Tesla mania. Woo! 4 Tesla. So the strength of that field up top there is 4 Tesla. But what about down here below? What do we got? We have B2 is going to equal the amount of magnetic flux over the area down there. How much flux do we have down there? 4 Webers. What's the area down there? 4 meters squared. So what is that going to come out to? 1 Tesla. So that field is a lot weaker down there. You could either say its magnetic field strength is 1 Tesla, or you could say the magnetic flux density is 1 Tesla. Do you guys remember this formula from last year? Vaguely, vaguely? Yes? Huh? it turns out if we take that formula and we solve it for the number of flux lines, what does the formula end up equaling? The number of flux lines equals B times A, like that, yes? And this basically tells you how many flux lines are going through a particular area. But this formula in its simplicity is for the ridiculously simple case of the field lines going perpendicularly through the area. And that's not always the case. So, say for example I have field lines going like this. If I have an area that's perpendicular to that field, I want to draw it like my hand here, perpendicular like this. So here's my attempt at a three-dimensional diagram. So here we go. I'll draw like. And then you know what? I'll put the red lines going solid through here. So they're going through that area. Well, here you would just use that top formula right there. But what if I turn my hand like this? I still have that same area, yes? So here I have the same field lines going here to the right. But now I have the area like this. So over here, the flux lines equal the strength of the magnetic field times the whole area. But over here, the flux lines going through that area, how much flux is going through that area? Zero. No flux. So we see that there's going to be like a trig function here, yes? But this is kind of bizarre because area is not a vector quantity. But yet we want to give that area a direction? What? So watch very, very carefully. What we're going to do is we're going to define a normal line to the area. And we're going to make it a unit length. A normal line to the area. So here's a normal line. Here's a normal line to this area. And then we're going to define a unit vector. Remember, unit vectors don't have any dimensions. They don't have any magnitude, or a magnitude of 1, that is. And it's just going to be a unit vector going in that direction. So I come over here and draw it in green here. I have a unit vector n. Does anyone remember how to indicate a unit vector? There's a special symbol. Instead of putting an arrow on top, which is like the symbol for any old vector quantity, if it's a unit vector, it's called a little roof. Caret. Nice. So over here we have a little unit vector like this. Now, if we multiply that little normal line, that unit vector, that little normal unit vector n times the area, what we did was we just gave the area a direction perpendicular to itself. So if we take the area and we multiply it by that little unit vector, we kind of made the area into a vector quantity with a direction perpendicular to itself. And if you want it to be technically correct, you should always write this, a times the unit vector for the normal line. But hardly anyone writes it that way. The sloppier way of writing that is they just write it like this. They say the area, like that, which is kind of a little misleading because area is not a vector quantity. So if you ever see like the area with a vector sign above it, what they're really talking about is they're talking about like the size of the area times a unit vector perpendicular to it to give it direction. Now notice in this case to the left, this case over here, what's the angle between the normal vector to the area and the electric field lines? What's the angle between this unit vector here to the area and the electric field lines? It is 0. And over here, what's the angle between the unit vector to the area and the electric field lines? And here we just want to multiply the two together, and here it ends up being 0. So what trig function are we going to add to our formula up here to cover all the angles? And of course, the angle in between. What is going to be the formal blown out version of this? BA, is it sine or cosine? And how do you know it's cosine theta? Exactly. 0 degrees, cosine of 0 is 1. 90 degrees, cosine of 90 is 0. So theta here is the angle between the normal to the area and whatchamacallit, the electric field line direction. But we've seen that before. BA cosine theta, or that format. Work is another example of this. This, in general, though, if you have like this vector times that vector, and you get this, the magnitude of this times the magnitude of that times cosine theta. Can anyone read your physics teacher's mind? It's a dot product. That's a scalar product. So we can come back over here and say it's the dot product between the magnetic field strength. Oh, guys, you haven't been correcting me. What did I just say? E, we're doing B here. We're doing magnetic field strength. Right. So it's a dot product. And what are the units for magnetic flux? Webers. The number of Webers going through the area. Now, it comes up later in magnetism. Sometimes you don't want the magnetic field strength. You don't care how strong the field is. You're more concerned with how many Webers the conductor is busting through. Do you remember what I'm talking about? If you have magnetic field lines, and you have like a wire conductor that you're gonna be slicing through. And these are magnetic field lines B. Do you remember what ends up happening in that wire conductor if you bust the flux? You take a wire and you physically bust through the flux. You move it through the magnetic field lines. You get a current due to a voltage. Do you remember Faraday's law says that the induced voltage, the EMF, it's equal to the number of flux lines busted divided by how much time? This, of course, is in volts. But what is a volt actually equivalent to then? A Weber per second. Study your E-cases.